right? So probabilistic model, right? In that we have what is called the combinational model, and then we have what is called the sequential model. Sequential model example what we discussed was this HMM, hidden Markov model. Combinational model, the example is this Gaussian mixture model. This is very simple combinational model when you compare to the sequential model, because sequential model, we have a sequence, right, is taken to account x1, x2, x3, and so on up to xn, and we exploit the property that the relationship, right, how far this correlated, the x2, how far it is dependent on x1. That information also we are actually taking into account for, right, the model, probabilistic model in case of the sequential case. But in case of combinational, these these vectors, whatever we are getting generated from the model, they are totally independent to each other. So in that case, this becomes very simple, right? So these vectors, x1, x2, everything is going to get generated independent. But the term combination is coming into picture because, and this x1, x2, x3, the sequence we are not taking into account, but still we are going to have multiple Gaussian. It is not going to have a single Gaussian model in it, right? So it is like the vector x1 is getting generated, right, as the linear combination of, right, getting generated from three. For example, in this case, I have chosen three Gaussian model. So this is that Gaussian model 1, and this is 2, and this is 3. It means that it is going to have its own mean, I mean, that covariance matrix, which is described by this mean and covariance matrix here, mu2 sigma 2 and then mu3 sigma 3. In this case, the arbitrary probability, right? So probability of x, some vector, right? Probability of x is actually getting generated as a linear combination like this. Say, for example, in this case, right? If you write in expanded form, pi 1, probability of x getting generated with the model 1, I mean with the first Gaussian model, which we can write as explicitly like mu1 and sigma 1, right, plus pi 2, probability of x getting generated with what, mu2 sigma 2, and then pi 3 of, into this probability of x getting generated with mu3 sigma 3. This is what we say that it is the combining three Gaussian here, Gaussian mixtures. This is the first Gaussian, we have a second Gaussian, and we have a third Gaussian, right? The vector x, the arbitrary vector x, is actually getting generated, right, by all these Gaussian model with different probabilities. So that is what the idea is. The idea is it's a linear combination. That's what we are doing. So we call this as a combinational model. We have different responsibility. We can say, we can introduce a term called the responsibility factor, right? That responsibility factor is something like which Gaussian model is more responsible for generating a vector x, right? Because the vector x could be generated from the model 1, I mean Gaussian model 1 and 2 and as well as 3, because as you know, this model dies only at infinity because we have a mean here, right? So this ellipse is not actually stopping here. So this is just a representation of this Gaussian density function, but this ellipse actually is, we have to keep on drawing this ellipse we have to plot like this, and it goes only right at infinity. And this also, we have a ellipse like this. Only mean is different, right? So, but you get this ellipse and it also goes up to this infinity. We get the region where overlapping will also occur in this, right? So overlapping also will occur in this. So what I'm trying to say here is all these three Gaussian model is actually responsible for generating this X, right? And this probability pi1, pi2, pi3 will give you the information which is giving you the most important contribution to that for that generation, right? So suppose that if this pi1 is 0.9 and this is 0.1 and this is 0.1, we can say that that vector, this Gaussian model 1 is more responsible for generating that vector, and other tools are also involved in it, but that responsibility is less, right? So this is what we call this as Gaussian mixture model. In other words, the reason is that density function, for example, in case of single variable, right? Single variable, if I plot the histogram, right? Suppose that if I have a single peak in it, we can try to model them as a Gaussian, right? We can model them as a Gaussian by fixing some mean and variance, right? Suppose that if it is 1D case, I'm telling 1D case, if I'm just plotting this histogram, of course, I have drawn this one in a continuous fashion, but remember that it's sort of discrete case, right? So it is like that. Okay, so which follows some shape like this, so we can model them, right? So what I'm trying to say here is the histogram, and we are modeling them as we are approximating that one as a Gaussian in this, right? For single peak, it is okay. Suppose that if I am having a data X, and if I am plotting this histogram, which ends up with multiple peaks like this, right? We cannot fit this model. This is the histogram what we are getting in practice, right? So in that case, we cannot fit with single Gaussian. We have to necessarily go for mixtures of Gaussian. This is one Gaussian. This is a second Gaussian. This is a third Gaussian, right? So it is something like it is a mixtures of this one, and we have this another Gaussian like this, and we have the another Gaussian like this, right? So if you want to consider this, you can consider or you can leave it. So in this case, let us say it is a mixture of 3. So it is a Gaussian mixture, 1, and we have 2, and 3 Gaussians are mixed together to get these 3 peaks. Suppose that if I have a histogram that has these multiple peaks like that, and you want to model them as a single density function, then we have to go for what is called, right, Gaussian mixture model. And that's what I said. And we have, it is described by its mean. And if for 1D it is a variance, for higher dimension, we have covariance matrix. And then for the second Gaussian, we have this mean vector mu2 and covariance matrix sigma 2. And for the third case also, we have a mean vector mu3 and then covariance matrix sigma 3. All right, and this is the model, right? So now the question is, right, given the data, you will be given only the data. I mean, the data means, you know, what I have plotted, this histogram is from the data. You are given only this outcome. You are given an outcome here, X, right? So for example, Xn. So this is not sequence here. It is just the vectors, what is given to you. And you need to model them using this Gaussian mixture, right? So modeling means I am interested in knowing what is my mu1 sigma 1, what is my mu2 sigma 2, and what is my mu3 sigma 3 in this case, right? And that is what exactly we call it as Gaussian mixture model, right? Okay. To do that, we need to initialize. Even in HMM, I said that we need to initialize this value, mu1 sigma 1, mu2 sigma 2, and so on. First of all, we would like to know what is that mean, right? So we would like to know what is that mean vector and covariance matrix to be initialized, right? So which we do this one using what is called this unsupervised algorithm called k-means clustering. So what is given to you is just the data, right? So let us say that you have a data which is plotted in 2D space like this. This is what the data here. So you have a data. This is what is given to you. Now let me put it as class itself, because there is no indication about the class index, right? So it is basically the data what is given to you, right? So all are labeled in the same class like this, class like this. This is a 2D space having element X and Y here, right? So this is the 2D space, right? Visually, we are able to understand that there are 3 clusters available. Cluster 1, cluster 2, and then cluster 3, right? So we need to solve them. Actually, we need to know about this number of clusters. Once you know the number of clusters, then we can actually identify the mean and covariance matrix of the individual clusters, right? So this is actually class label. It is unsupervised algorithm, which one of the algorithm in unsupervised is your k-means algorithm. That's what we are actually discussing now, right? So what is that k-means clustering basically, right? So here we have k clusters, as you see here in this expression, right? So there are k clusters and you are given n vectors. Your goal is, right, you are constructing the objective function here, right? So that, the distance between the vector, you have a mean vector, right? So here, for example, this is the mean here, mu1, mu2, mu3, right? So the distance between the vector, what you assigned for the cluster 1 and with this centroid, that must be closer to each other. And this two needs to come closer to each other with this centroid. And these vectors need to come closer to each other with this centroid, what is called, these vectors are assigned to it, right? So that assignment is described by what is called the parameter R subscript nk. See, you see that R and K is taking either the value 1 or 0. It means that if it is closer to this, we assign 1. For example, if I have some arbitrary vector, say, for example, this is my arbitrary vector, I need to assign the value of k for it, right? I need to assign the value of, say, R11, R12, and then R13, because we have 3 class here, right? So how to do that? You are actually finding out the distance from this to this to this, and here this to this. And you are going to find out whichever is minimum. Suppose if this is the minimum, we are going to give the value of this R11. So say this is the first class, my cluster, and this is the second cluster, and this is the third cluster, right? So we have 3 variables, like this is the nth vector I'm talking about, xn, nth vector. So Rn1, Rn2, Rn3, right? If it is closer to this cluster 1, we give the value this as 1 and the remaining 2 values we keep it as 0. So that is the meaning of writing this R and K, right? So every vector, so even not only this vector, we can even take any vector here. For example, this vector we can consider. This is closer to this centroid. So we give this value, right? This say for example, this is of 10th vector, right? X10, 1, it is 1 here, and X10, 2, X10, 3, that those values are going to be 0. I repeat, I mean, not X, R, I'm sorry. So let us say this is the 10th vector, right? In that case, we have what is called R10, 1, R10, 2, and then R10, 3, because we have only 3 clusters. So this value is going to be 1 here, this value is going to be 0, and this value is going to be 0 in this case, right? So it is like that. So that is the value of this R and K. We are interested in actually finding out the value of mu k in such a way that this value is getting minimized. So that is the goal of the k-means clustering. So if I differentiate with respect to this unknown, which is mu k, and solve for it, you are getting this as a value. What is really it mean? Even though the expression says Rn k into xn whole divided by sigma n Rn k, it is like that. What it really says, intuitively, I mean, by this expression, we understand that Rn k is taking the value of n, I mean, 1 or 0. So it is basically, it is finding out the vectors belonging to that particular cluster, right? And then divided by the number of vectors in that cluster, right? So that is what really happening, right? See, some vectors which are closer to each other, they are actually grouped together and you are finding out this average, and that average is what your mean vector. And this cluster, the vectors after taking average, we get this mean vector mu2, and the vectors in that cluster 3 taking average, and you get a vector mu3 here, mu1, mu2, and mu3, right? So we can actually interpret in a different way how we go about this as algorithm, right? K-means algorithm. What we are going to do in this, very simple. What we have to do is, it is just like we are creating 3 bins, bin 1, bin 2, and then we have this three bins, and you are given a vectors like this, x1, x2, and so on, up to what? X, say for example, x100. There are 100 vectors given to you to do this task, right? So you need to cluster them, right? You are going to initialize first some arbitrary, it is totally random. What we are going to initialize is the mean vector, okay, mu1, mu2, mu3. These are all the mean vectors which is initialized randomly, random initialization. Then you are going to find out, you are going to take the vector x1, and then you are going to find out the distance between this x1 with mu1, x1 with mu2, and x1 with mu3, right? And you are going to find out whichever is minimum. Suppose that if the distance between the vector x1 with mu2 is minimum, you are going to put this vector in this bin, x1 here, and take the second vector, you put it in the corresponding box. So this is going to be your x3, and maybe this may be your x4, and this is going to be your x5, and this is going to be your x6. It is like that, right? So you are going to have this vector placed in 3 different bins, right? Depends upon the distance value, whichever is giving you the minimum value, right? So once you get all these vectors in the particular bin, you are going to take that average of all the vectors in this bin, and you get what is called a new mean. And this average will give you the new mean vector, and this will give you the new mean vector. Now the bins are emptied. I mean, there is nothing inside this bin. It is blank now. You are going to make it as blank now. So the bins are now empty, right? So once again, you're going to fill this bin using the new mean vector, what actually you got. You arrive with a new mean vector, then you are going to find out the vector is going to fill with these 3 bins, right? Now again, it's going to be randomly filled, x4, x7 like this, and this is going to be x2, and this is x3, this is x7, like that. And so it is randomly, I mean, based on the distance, you are going to have this values gets filled, right? X20, x24, like that. And again, once again, you have to take that average, you get a mean, and then you have to cluster them. It's keep on doing that. After some time, it gets converged. And in other words, your J value is actually getting minimized. There is no big difference, in the successive iteration. That stage, how exactly the thing is happened, right? So in this example, you see that this is the data, right? So this is the initial value, right? So how you see that how the cluster is happening at every stage, right? Right? It goes on like that, and you can see that after some iteration, how the clusters has actually getting converged, right? So this is the way how it gets converged in this, right? So in fact, it all depends upon the initial value of the mean. For the particular mean, what we have initialized, the cluster will happen. But just like any other algorithm, here also the local minima is what actually you will expect, right? Global minima is not guaranteed, right? Convergence will happen, but global minima is not guaranteed, right? So global minima means, is that the best solution of the clustering, right? So if that is a question, there is no answer for it. You get a convergence, you get some minimum value as the iteration goes, the j value will get actually decreased. After some time it gets stopped. After that it will not change. That time you will stop and you will say that cluster has happened. But is that the clustering the best? If that is a question, the answer is no. It all depends upon where you initialize, right? So we may need multiple initialization to do this type of task. We can even go for, right, the iterative method. I mean, the way what we have done, right? So the another way is, you can have other functions also, which actually measures how far this vector and the mean are closer to each other, right? So depends upon the other measurements also, like correlation, right? For instance, so depends upon that only we can actually go for the k-means algorithm. Depends upon that function, we say having a different thing in that, right? So this is a sequence algorithm where we get this steepest descent algorithm is coming into picture in this, right? I hope this is known to you, right? So this is the another way of updating the muse rather than going for whatever we had it earlier, right? So taking that average and all I said, right? This is the another way to update this mu k, right? So this is using the sequence least square technique of updating that. Okay, so let us consider this example. This example will give you the better clarity of k-means algorithm, right? So here each pixel, right? Each pixel is actually we have red, green, and blue combinations, right? So that only gives you the particular color. So for example, this is the original image. This every pixel is going to have red, green, and blue, and it is basically the three element. Each pixel is described by three element, right? So and each element can take the value red, green, and blue, and each element can take the value ranging from 0 to 255. It is like that. So G also takes 0 to 255, B also takes 0 to 255. Of course, we can normalize it. If you divide it by 255 in all the case, normally that is what it's being done, right? So you are going to have the range from 0 to 1. 1 indicate 255, right? So that is a gray value. So depends upon that particular combination, we get different color. So this is basically the image processing. Suppose that if I say 0.2, 0.3, 0.7, that determines some color. This determines some green color, green RGB. I mean blue dominated, and we get something green also. Red is very less, and then we get something like that. And suppose that if it is 100 is purely red, and if it is 010 it is green, and if it is 001 which is B, I mean blue here, right? So now what you are going to do is you are actually going to k-means algorithm, right? You are going to cluster this vector into two half, depends upon the number of cluster. For example, 2 cluster, and this is, we have 3 cluster, right? You see that we have different, clusters here, k equal to 10, and then we have the original. Just 10 clusters is actually happening here, and you are going to reconstruct the image using that mean vector alone. What does it really mean by that? It means that in this case, the pixel values will take either, one among the 2 values only in this case. Okay. So in the first case, the pixel values will take either mu1 or mu2. Only 2 centroids are there. And here we have 3 centroids, mu1, mu2, mu3. Each pixel, right, will take either mu1 or mu2 or mu3. That is what it's getting filled here. Here every pixel, it takes either mu1 or mu2, and we have 10 in it. And this is the original, this is going to be 255 levels. Sorry, 256 levels. 0 to 255, it is 256 levels. This is just 10 levels. This is 3 levels. This is 2 levels. That is the meaning of it. Right? And you see that 10 levels is not, bad, as bad, we are able to get somewhat, right, the information like that original image, except some pixelization. The color information also is not much lost. Only 10 levels will actually carry the information as that of, how the human are able to receive the color property, all those things, right? So there is some big difference. But 256 levels, you are getting like this. This is one example of K-means algorithm, how that clustering is happening, right? So this is what I said, these mixtures of Gaussian, right? So quickly we will see how this mixture model, this one K-means clustering is just to initialize this mean vector alone, right? So this will be helpful in case of HMM also. In case of GMM also, it is going to be helpful, right? So now we quickly go through that mixtures of Gaussian, GMM. This is a GMM model. How to get these parameters? You are given a data, right? So you are given x1, x2, and up to this xn. You are given this data, right? And let us assume that the number of states are fixed. K is fixed, capital K. The number of clusters or the states, right? It's clusters. In this case, we normally call it as a clusters, right? Or mixture, number of mixtures are fixed now. K's are fixed, right? So now, as I told you, this is what I gave the expression in the earlier slide in the expanded form. Suppose that if I have 3 cluster, it is the probability of x given mu k sigma mu1 sigma 1, and then pi 2, and we have this probability of x given mu2 sigma 2, and then we have this pi 3 probability of x given mu3 and then sigma 3. So this is the mixtures here. What you are seeing in this is the mixtures, and this expression is more general expressions. The linear combination of 3 mixtures is happening. K mixtures are happening in this, right? Just like HMM, this is even simpler than your HMM, right? The trick is the same, the idea is the same, the flow is the same, right? Here we are going to introduce what is called the latent variable Z, and which is going to generate your X. But this model is comparatively simpler because there is no change in the state is happening, right? So Z1 responsible for generating X1, Z2 responsible for generating X2, Z3 responsible for generating X3, and there is no link. This link is not there. In HMM, we have this link. That is that sequential model. This link is not there. They are separated. All the vectors are getting generated independently, right? So that is the major difference, and that makes the problem still very simple to solve in this. But remember that this Z1 is a latent variable, and again this is going to be take the value like, right, like, for example, if it is a 2 mixture, it takes either the value 1 0 or 0 1, right? It is from the Gaussian model 1, and this is the Gaussian model 2, right? Suppose that if I have 3 mixtures, it is going to have 1 0 0, 0 1 0, and 0 0 1. It means that the vector x1 can generate either from mixture 1 or mixture 2 or mixture 3. It is like that. X1 can generate from either 1, Gaussian, right? 1, 2, or 3 here, right? So that is that Z1. There is no link between Z. That is the only difference, right? So in this case, what is that our objective function? Our objective function is again the generating probability of X, right? Here that, probability of X is probability of X1, X2, and then X3. This is what you are going to maximize, right? But this can be written very simple in this case, right? You are going to write it as probability of X1, X2, X3 given Z1, Z2, Z3 into probability of Z1, Z2, Z3, and taking the summation over all values of Z1, Z2, and Z3, right? So if I treat this X as a vector, X1, X2, X3 combined together as the vector X, and Z1, Z2, Z3 combined together as the vector Z, right? So this bold letter is the vector here, right? So you are writing this probability of X is a vector in this case. This is probability of X1, X2, X3. That is the meaning of it, which is written like probability of X given Z into probability of Z and taking the summation over Z, right? So we are writing like this. This is what we are trying to maximize in this problem. Mixtures of model, this is what you are going to maximize, right? And which we can write like this, exactly the same technique we are going to use, as Zk is taking either value 1 or 0, right? We are able to write probability of Z as the product K varies from 1 to K, and this is that prior probability pi K, right, power Zk, right? So depends upon the value of Zk. Suppose we have this Z1, if it is 1, then only you get this pi 1. Other values are going to be 1 in this, right? So the same trick how we adapted for HMM, right? So it is like, suppose that if I have 3 state, it is written like this: pi 1, pi 2, 3 mixtures, pi 1, pi 2, pi 3, and power Z1, Z2, Z3, but it takes any one of the value, right? So what I'm trying to say here is either Z1 is going to be 1 and this 2 will be 0, or this one or this to be 0, or this one or this to be 0. Depends upon the combination, only one will get highlighted. Either pi 1 will come, or pi 2 will come, or pi 3 will come. So this probability of Z, that particular vector Z, can be written in this form, right? And right? So that probability of Ex, the vector getting generated when the mixture is 1. Mixture is from Zk means depends upon the value of K being, Zk being 1, right? If Z1 is 1 means first mixture, Z2 means second mixture, Z3 means third mixture. Depends upon that, you get the corresponding mean vector and the corresponding covariance matrix. So your probability of X given Z can also be written in the same trick. We are going to have a Gaussian density model here. Power your Zk. Zk can take either 1 or 0, but it takes only one among them is going to be 1, right? Other things are going to be 0. So only one will get highlighted in this, right? So we are going to plug in this one in this expression, this probability of X given Z, right? In this expression, and then we'll see what is going to happen. Right? You see that we are going to maximize this. Just like what we did in the HMM, right? Here we are going to maximize this generating probability, but you are going to take that logarithm of the generating probability in this, right? Okay. So if I do so, if you are taking this in place of this probability of X given Z, we are going to substitute this pi and take this logarithm, right? You see that? We are going to take this logarithm of that, and that becomes summation. So the inner summation is, you are having this sigma k equal to 1 to k, this inner summation is coming as it is. And this, the outer summation is actually, right, is because of this logarithm, this product is actually becoming the summation here, right? So this is what this modified expression to be maximized, right? So it is like the ln of the probability of x1, x2, x3 given this, the parameter, right? Given the model, that is going to be the maximized, the generating model. This is what you are going to have, that maximization, right? So this can also be solved. I mean, modeling means we are interested in getting your value of mu1, sigma 1, mu2, sigma 2, depends upon the number of mixtures, right? Mu k, sigma k. Getting these unknowns is actually modeling, just like HMM. Here also we are going to have this as a model, right? So here also we are going to have what is called the expectation maximization algorithm. I'll just show you that, right? In case of HMM, we had that gamma and zeta and all was there, but in case of GMM, we have only one gamma. Gamma alone is enough, right? So this is the stage of, you know, expectation here. This is the stage of expectation, right? Where we get that value of mu k and sigma k in terms of gamma, right? So in GMM, still we have what is called expectation maximization algorithm, but in the expectation stage, we have only one parameter, not very complicated. Like HMM, we have this gamma alone. Maximization will end up with mu1, sigma 1, right? So that's a model of the GMM, right? So in fact, mu k, sigma k for all values of k's, right? So let us say if I have k states, you have this k up to this k, right? Like this. And this will help you to estimate this gamma, and you get this as a iterative thing, right? So here also we have expectation maximization algorithm. In the expectation stage, we have this gamma alone, not like HMM where we had gamma, zeta, alpha, beta, everything will be there. I'm just comparing that. So in case of HMM, we had these other other parameters like, you know, alpha and beta will give you this, and this will give you that. That is about this HMM. But in case of GMM, it's only one parameter we are having, right? So gamma alone, right? So which gives you mu k sigma k, which actually gives you the gamma. It is in the iteration stage, right? So what we are really doing here is we are actually differentiating this. There we had objective function, right? Here, this is the objective function which you are trying to maximize. This is what actually your objective function. You are differentiating this one with the unknown parameter and equal to 0, right? So if I differentiate with respect to mu k and if I equal to 0, you get the result mu k and sigma k in terms of this gamma by introducing the parameter called gamma. And this is what we say that it is gamma here. This is called this gamma, right? Gamma of z and k. We are introducing that this is as a gamma here, right? So using this gamma, we are getting this mu k and sigma k, and you have a expression for, right, that gamma. You see that because I gave the definition here itself. This is the gamma here. You write it here. This is that gamma, right? So this gamma depends on mu k and sigma k here. You see that this gamma depends upon mu k and sigma k. That is what we are going for, this expectation maximization algorithm. So the latest mu k and sigma k will determine you the latest value of this gamma, new value of this gamma, and gamma will help you to get back your mu k and sigma k. It is in the iteration, right? So this expectation maximization algorithm, it becomes now very simple. You are going to initialize the value of this mu k and sigma k, and in the expectation stage, you are going to get this gamma value, and in the maximization stage, you are going to get this mu k, sigma k, and then pi k, right? So all depends upon what? Gamma. All depends upon this gamma, and even your nk depends upon your gamma. You see that, right? It is like that. And then you are going to find out what is the likelihood function, which is actually in the loop, which is actually these 4 steps are in the loop until this log likelihood function is actually getting maximized, right? So this is still in the loop here, right? It is in the loop 1, 2, 3, and 4, which is in the loop until it gets converged. And then finally, what you have to get back is your mu k and sigma k. And that is what the model of your GMM. There we had many other parameters, transition parameters also there. But in this case, GMM, we have only mu k and sigma k that describes this model, right? So you can see this example here, how this GMM is actually doing that model in this, right? What is that, This is the initial case. We have that initial model. Initial model means what? We have a mean vector and we have that shape. Shape means the covariance matrix is actually initialized. The circular means the covariance matrix is basically the diagonal elements are same and it is going to be equal also, right? And this is actually describing you that, right? And it is not tilted. So it is diagonal. It is uncorrelated also. This is the initial Gaussian model. This is the Gaussian model 1 and this is the Gaussian model 2, right? These two are getting mixed. This is the initialization, right? And now as the iteration goes on, right? So you can see that this is actually the model what we are doing. These vectors is the model grouped here and this is grouped in this. So we are able to get this as a Gaussian mixture. We are having only two mixtures here. We are having only 2 mixtures in this example, right? And what is this color shades in the intermediate stage, which actually gives you the responsibility factor. Responsibility factor in this. Right? As I told you that all the vectors are getting generated by both the Gaussian model 1 as well as Gaussian model 2. The mixtures only is happening. And if it is pure blue, we say that the model 1 is responsible for generating that. If it is pure red, then we can say model 2 is responsible for generating that. But whenever if you see mixture color in the middle, right, somewhere in the middle, you can actually see that mixture color. It is a combination of red and blue, different shades available in that. In those places, those vectors actually both are responsible, for generating that. So that responsibility factor is getting shared in it, right? So otherwise, we get, if it is a pure blue like this, mixture model 1 is purely responsible for it. If it is purely red, is also no problem. This model is responsible for it. But as the iteration goes, you are able to get a proper separation. I mean, like model 1 and model 2, but we can say this is in the 5th iteration. Still, we have some places, both are having, both model is actually responsible for generating these vectors. Here also I'm seeing that, right? This is a different color in it, right? And the color shades are given purposefully to indicate that, basically. You can see this, how the separation is happening. This is a 3 mixtures in this. This one, the bottom one, is of 3 mixtures. This is the original data. Original data means we are purposefully generating the data from the Gaussian mixture model, which is having 3 mixtures. This is the data generation. We are generating that with 3 mixtures. We are purposefully generating, and then to the GMM algorithm, we are hiding that. We are not telling which mixture is of which group. We are simply giving only this as an input to this GMM model, and GMM model is able to get this. This is almost like the original. This is the original, and this is the capacity of GMM. This is that power of GMM. It is able to get it at 3 clusters like that original. But you can see in this, there is a color shade here other than red and green. These are all the places where the responsibility factor is not purely red, right, or green or blue. We have a mixtures in it, right? Both red and green are responsible for generating this. Green and blue are responsible for generating this. We have a color shades in it. Other than that, but here you can see it is original. As this is the original, we can have only pure green and red in this. But when you see here, we get some sort of different shades also coming into picture in this case, right? So this is the example to understand, right? So as you know that there's this responsibility factor, this gamma, right, is actually giving you that shade, right? Because gamma of zk equal to 1 given x, given vector, right? What is the probability that zk equal to 1, right? It means that you have that either the first Gaussian mixture or the second Gaussian mixture is going to be 1 or 0, right? So what is the probability that the first one is going to be 1 and the second one is going to be 1, right? So that is described by this gamma. In fact, this gamma only is giving you the information about this responsibility, and hence this is otherwise called the responsibility factor. Gamma is called responsibility factor, right? So given x, what is that? It is that Zn equal to 1 given x. So that is, I'm sorry, probability, right? I'm sorry. So probability of Zn equal to 1 given x, right? So this is the responsibility factor here, right? So it is going to be the partition only. If it is a 3 class, the responsibility factor, for example, if it is 0.7, say 0.22 and then 0.1, summed together, it is going to be what? 1 in this case, always going to be 1. It becomes a partition set, right? It means that mixture model, one is having more responsible for generating that vector X, and followed by that mixture 2, and then followed by mixture 3. So you can even have the values like this, 0.7. So see, we take 0.1, 0.7, and then 0.2. Yeah, 0.2, right? So in this case, mixture model 2 is having more responsibility factor. So you can even have pure 100. In that case, mixture model 1 is actually having a pure, responsible for generating that particular vector. So that color shade is what actually giving you here for visually to get it understand. Right? So nothing else. So here you are getting that for every vector, we have 3 elements of responsibility factor, right? So this is only the indication how the algorithm is powerful. Your GMM is able to do this. That is the thing for here like that, So here it is given in the last final stage of iteration with 3 cluster. But in this case, every stage you can see how that is happening, right? So after 20 iteration, how that Gaussian mixture model is able to achieve this, that you are able to see in this, right? So with this, actually GMM is getting over. So we have completed this course successfully, right? So I will actually give you the page numbers or in my book, whatever is there for the, for the end semester. So you can go through that. And